Okay. Hi. So you saw me on the first day of class, so I'm stepping in for a few lectures. Anybody like the fast Fourier transform last time? Somebody? Most of you don't raise their hands. I guess that's good. We're changing topics today. It used to be we dedicated 2 lectures on fast Fourier transforms, and we confused people more than with 1 lecture. So now we just spend 1 lecture on a fast Fourier transform. The rest, please make sure to practice it in discussion sections and exercises. There's multiple ways to view it, not just through the matrix view with submatrices, also with coefficients, even and odd if you're familiar with the various ways of understanding fast Fourier transform, you can stick better. But so far, we're going to leave behind I guess a lot of the divide and conquer type of problems that we have been looking for a few lectures. We're primarily looking at ways of multiplying things, whether it is integers, of matrices, or polynomials. And so the primary approach there was divide and conquer. For the next few lectures, we'll be doing a unit on graphs, okay? Looking at connectivity today. We'll be looking at shortest paths for a few lectures after that, okay? So it's much more sort of combinatorial type of problem, okay? So next few lectures, the plan is graphs. So maybe before we spend a few lectures on graphs, maybe we should at least clarify to ourselves why it's worth to look at them. Why should we ask computational problems about graphs? Anybody want to offer some suggestion why graphs are interesting to look at? Yeah? Sorry? We can use them in machine learning, yes. It sounded like the answer is kind of almost rhetorical, right? So graphs are an extremely powerful modeling sort of tool, right? You can model scheduling constraints, right? You can model your brain. The internet is a graph, right? The social network on Facebook or various social media are also graphs, right? Roads that you travel through is a graph, right? So if you're able to kind of abstract away the details and sort of represent your problem instance as a graph, then presumably the question you were trying to solve about kind of whatever it is you were looking at can also be phrased as an abstract question about a graph. So it's like a very clean, powerful model, a combinatorial model that shows up all over the place, okay? So that's why kind of we look at it. And so just don't underestimate the modeling power of graphs. So formally, you should have seen graphs before, but nonetheless, in order for us to have a common language and notation, let me just go through the motions of telling what is a graph mathematically. It is a pair, okay, of 2 sets, okay? One is the vertex set. It is just a set that represents the vertices. The other one is the edge set, okay? It is some subset of all possible pairs of vertices, okay? So mathematically, it is just a pair that has this property. When we talk about graphs, there are usually 2 types of graphs that we think about. One is undirected graphs. That means that if you look at the edges, any edge can be somehow traveled in either direction, okay? So one way to say it mathematically is that if u and v is an edge, then it must also be the case that vu is an edge, okay? Or maybe uv was never an edge, then we don't say anything, okay? Otherwise, we talk about directed graphs, okay, where we don't impose this relation. For example, if you consider abstractly the brain, it would be more of a directed type of graph, right? Because synapses kind of operate in one direction, not the other way around. As a maybe bad analogy for undirected graphs, most roads can be traveled both directions, usually with the same cost. That's not always the case, but maybe you can think about as a perfect road network as an undirected graph. can travel both directions. And of course, that's not literally true. You have one-way roads. You have two-way roads with different costs in each direction, like the Bay Bridge. You pay only one direction, not the other way around, right? And graphs behave rather differently in the two cases. So when you are thinking of problems or modeling, it's certainly one of the things that you want to think about right away. Are you modeling your problem as an undirected or as a directed graph? Another thing that is important to have in mind that probably you've seen, again, before, but in this class is important to clarify, is our notion of efficiency is measured in relation to what for an algorithm? The input size, right? So the fact that I've defined a graph mathematically is still not quite, doesn't still give me like a concrete handle on what is it really when you feed it as an input to an algorithm. Remember that in order to understand efficiency of an algorithm, you need to literally understand like what bits are you taking as input. As an analogy, when you talk about multiplying integers, you had to clarify to yourself, well, okay, I'm going to write them in binary notation, and I'm going to be efficient relative to the binary representation of the integer, right? So similarly, when you have a graph and you talk about computational problems, you must clarify to yourself what is the representation of your graph, okay? Because then everything will be measured against that. And there are two kind of canonical representations of graphs that you may encounter. One is called the adjacency matrix representation. So you have some matrix of the graph, okay, that it is the vertices index both the rows and columns, okay? And so basically, inside this matrix, you will find an entry for every possible pair of vertex, comma, vertex. And you just put a bit or a 0, depending upon whether the edge represented by that location, maybe u, v, really is in the edge relation or not, okay? So you just basically put down all possible edges, and you mark with a bit which edges are there, okay? So this is one representation that fully specifies a graph. Do we agree? By the way, if the graph is undirected, how will this matrix look like? It will be symmetric, right? Cool. Okay. Again, this should be a review for most of you. At some point it will be a transition, probably towards the end of this lecture. Next few lectures will get sort of new material, so we need to make sure that we're all on the same page with this basic material. Then we also have the adjacency list. So that is a list. So you basically write down the list of all vertices. So 1, 2, so vertex 1, vertex 2, vertex 3, and so on and so forth, up to vertex n. And for each one of them, you list their neighbors. Okay, so for example, vertex 1, maybe he is adjacent to vertex 3, 7, and 10. So there they go, right? 2, maybe he is adjacent to 1, 6, and 9, okay? And so on and so forth, okay? So for each vertex, you just list all the neighbors. Maybe they're sorted, maybe they're unsorted. This is kind of, we're getting a little bit too detailed into the data structure, but these are two canonical ways to represent graphs, okay? Now, just so that we understand them, so even in this class, you may sometimes choose one or the other, or maybe asked to think about one or the other. It is important to be clear about some of the trade-offs that each of these present, right? Because, again, how you choose to represent your input has impact on how your algorithm can efficiently reason about it, right? So the trade-offs, well, it really depends on what questions you want to ask your input, okay? Typically, the types of questions that an algorithm may ask the input, one of them could be, is a particular edge in the edge set, for instance, right? The algorithm may at some point, it's computing, at some point says, oh, I wonder if this edge is in the edge set. Let's go look up in the input, right? That would be one type of question. Another question would be, what are the neighbors of V, Okay, please return to me all of the neighbors of V. Another crucial thing is, of course, how large is the representation itself of the graph, right? Because efficiency is relative to that. So we can just very briefly compare, but these are not necessarily the only questions you may ever care about. This is just an illustrative sort of examples of questions you may have about the input. We can compare what happens in the matrix case and in the list case. How long would it take for me, given a matrix representation or graph, to answer this question? Oh, 1, right? So by the way, we are assuming some random access to memory, right? So we're not on a tape or a Turing machine. You know, we have like random access memory, and so we just go directly and see is the bit 1 or 0. What about the neighbors? So I have a particular vertex, and I want to collect all of the possible neighbors. How much will it take me? O of V, right? Also, maybe I'm going to introduce the 2 letters that we're going to use. Primarily, when we talk about graphs, N will always denote the size of V, and M will always denote the size of E. Okay? So here, let's call it order of N. Okay? How much space does the matrix occupy in memory? N squared, right? Notice that if you have an n squared algorithm, given that the input is of size n squared, that would be a linear time algorithm, right? All right, so for a list, when I want to answer a question, is an edge in the edge set, how long will it take me? Yeah, in the worst case, order of n. So let's write it. I can say something slightly better, because if I know that the graph, every vertex in the graph has a small number of neighbors, really, I can do order of, let's call it d, which is the degree of the graph, OK? The maximum number of neighbors that any vertex has, OK? Because why? Because the list here is only going to include order of d, OK? What about neighbors? Yeah, so this goes into data structure. It's either O of 1 or order of n or order of d, depending upon what you mean, right? Because order of 1 would be you just return a pointer to the list, right? But if you have to physically take the list and like return it, that would be a list of size order of n, or if you have a bound order of d, right? So since we're not really talking about pointers in this class, I'm just going to write similarly to the previous line. If you don't have a bound, that would be order of n. Otherwise, in the worst case, you have to like physically take the list and return it. That would be order of d. If you can just return a pointer, that's kind of order of 1, right? The interesting thing is that the space here, now it is different. That would be order of what? M, right? Because kind of every edge appears as induces one entry in this list, and together you have order of m, right? So when should you pick which representation? Well, first, you may have external constraints. Maybe a problem set tells you to use one or the other. But if you're by yourself and you're making a choice, typically the adjacency list representation is for so-called sparse graphs. So these are the graphs where m is much smaller than n squared, right? But if your graph is dense anyways, you don't mind writing down all this information. In fact, you will get some advantages like this one, for instance. You have a hit here, but this often is pretty good. Okay. All right, so this is just a review. Keep in mind that anytime we're discussing an algorithm, underneath it all, there is some representation. Okay? OK. All right, so today's lecture is going to be about a particular class of problems about graphs that have to, yes, there's a question. Yes, I will write bigger. Thank you. Today's class will be about a class of problems that have to do with the connectivity of graphs, OK? So and anytime we talk about connectivity, there is a particular algorithm that, or at least family of algorithms, called depth first search. Depth first search, also known as DFS. It's really a family of algorithms. that collect information for us, okay? I believe many of you should have met in some way the depth first search in other class. That's correct? Okay, cool. We'll be using DFS in many contexts in this class, possibly some that you haven't encountered before, so make sure pay attention today. So before we actually get to depth first search, I want to take a small detour to discuss the main subroutine of depth first search called explore that we'll be modifying in many ways to do useful things for us. And I also want to give an example of a type of proof that one often does about graphs, okay? For correctness of algorithms, okay? So we're going to look at the explore procedure. It is a particular subroutine. It takes as input a graph and a vertex in the vertex set, okay? And its goal, the goal, is to kind of mark, kind of see all vertices reachable from V. Okay, so somehow there's a subroutine, kind of you spawn the subroutine at the vertex V, and the job is for it to figure out what are all the vertices that are connected to V. Maybe they're very, very far away, but they're connected to it, okay? It's a pretty simple subroutine. First, when you run it, it will mark where you spawn it. Okay, it will say, I am at V, so I will say that I have visited it. So you're kind of marking it, I've been here. And then you say, for each outgoing edge, VU, if you have not visited the other edge that you get to, if not visited U, then you explore it. Okay? Now, intuitively, this is a simple piece of pseudocode. Should be kind of clear that, if you run this, you will, kind of mark V, then you start marking U, then you start marking further on in case you haven't marked them yet, right? And clearly, at some point, it will halt because, it just doesn't move unless it meets a vertex that is unmarked, okay? What I would like to do now is take this very simple piece of code and prove a simple lemma that actually formally says it does visit every vertex reachable from V, okay? So you can see an example of the types of proofs that you can do in graphs. Is that okay? Any questions about the pseudocode itself? I mean, it's pretty simple. But this is not necessarily super useful on its own. Why would we mark all the vertices reachable for V? That doesn't seem like a very useful task. But pretty soon, this is a very useful subroutine. All right. So let's prove the following claim. The explore GV visits every node reachable from V. Okay? All right, so proof. You will find yourself many times writing an algorithm and say, well, yeah, obviously it works. Sometimes you'll be right. Other times your intuition will have brought you astray. And so that's why you need proofs to convince yourself of that, right? In this case, and especially in graphs, it's very useful to kind of proceed by contradiction. OK? So suppose not. OK? This potentially very obvious claim, suppose that it's false. We ought to be able really to find a contradiction somewhere. OK? So, let, how do I call it here? A be a vertex that is not visited. And is reachable. That is the instance of the suppose not, right? There is a vertex reachable from V. Okay, and it has not been visited by explore. All right? So here's something you can do to reason and kind of really see the reason why this code works. Take the vertex V and the vertex A. Now, we know that A is reachable from B. So there is a path that goes from B to A. Right? Now, this path may have absolutely nothing to do with what Explore does, but it exists. Right? Now, V is visited, A is not. So let's look at the first time along this path, okay, that we find a vertex that is not visited. Okay? Let's call this B. B is the first vertex along this path that has not been visited. That means that the vertex immediately before it, let's call it W, has been visited. Right? Now, the only way that W has been visited is through that line of code up there. It says it set it to true because at some point, Explore was run on W. That's the only way they could have been visited. Right? Now you see, OK, that means that that piece of code was run on W. So let's see. OK, it set visited W equals true. Great. Next line of code, it says for every outgoing edge, OK, every outgoing edge, if one of them is not visited, it should explore it. Well, look, here there's an outgoing edge, and B has not been visited. Well, but that can't be, because otherwise we would have run explore on B, right? So what we've done here is taken like in a rather kind of simple claim that in this case it's not to be right, and you may have like had strong intuition it's correct, but we've turned it into like a rather formal claim. Now I didn't write down all the sentences that as I said, but you will agree that this claim certainly is sharper in your mind now than it was before, I hope. Okay? All right, so this is just please keep in mind proofs by contradiction and considering paths, okay? Because graphs are kind of hard to see in your head, right? It's like, how does an abstract graph look like? It's just a mess, right? But you can focus on it, on some piece. Usually proof by contradiction lets you kind of get a handle on something interesting inside the graph, okay? Because by contradiction, something interesting is happening. So you just zoom in and you talk about that, right? Yes? Because we ran explore on, so the question is, why did we run explore on W? Because we said W is visited, because B was the first unvisited vertex. W must exist, because in particular, it could have been V, right? So the only way that W could have been visited is because explore G, W was run at some point. I don't care when, right? And then we get contradiction. Okay? Yes?
How do you know that B is?
Because it could have been A. I assume that there is a vertex reachable from A. So the question was, how do I know that B exists? It's a good question. Right? You shouldn't just conjure things that help you in the proof. You need to make sure they exist, right? We have assumed by contradiction that A is a vertex reachable from V that is not visited, right? We just make sure we pick the first unvisited one, right? Because maybe all of these are not visited. If I try to pull this argument on A, it wouldn't work. It's important that I pick the first not visited one to make sure that the previous one has been visited, right? Again, like I encourage you, as simple as this argument is, just write it out formally, maybe at home, carefully. You'll be doing like similar things on much less obvious algorithms, okay? Okay, cool. So this is the explore subroutine. Now let me come back to DFS. And say, what is the algorithm DFS? Okay, so DFS takes as input just a graph, no vertices, it's just a graph, okay? What does it do? First it says, for every V in the vertex set, so for every vertex, you're first going to set the visited flag to be false. Okay? So you just initialize an array of false visited flags. right? And then for every v in V, if V is not visited, then you explore it. So hence, we're using this subroutine. OK? DFS, what it will do, it will paint, will mark all the graph, all the vertices in the graph. OK? Is that clear? It should be, right after we prove that one. It is also clear that this algorithm is really useless, right? I mean, if all I wanted was to mark all the vertices in the graph, I didn't have to do it in such a Baroque way. I just kind of take them one at a time, I mark them, and I'm done, right? But the point is that this skeleton of traveling the graph in this particular way, we can actually piggyback on this skeleton to kind of add bookkeeping information. And this bookkeeping information will give us insights into the structure of the graph, OK? But are we comfortable so far with this kind of useless algorithm? It's clear that it will mark everything in the graph, right? Intuitively, kind of you start on somewhere, it will explore everything reachable from it. Maybe something is not reachable from it, so we'll start again somewhere else, right? And then whatever has already been touched, you don't explore it. Otherwise, you never halt. Another thing that I should clarify before we move on to bookkeeping is I want to spend just a few minutes talking about the running time of this algorithm, OK? This is a recursive algorithm. You have seen recursive algorithms several times in this class. And what techniques have you used to analyze the running time of those algorithms? Solving recurrence relations. To analyze this algorithm, that's exactly what you do not want to do, OK? You will get like a horrible running time if you use that. Instead, you have to use a more global type of accounting. So I just want to quickly do it on the side to see what is the running time of this algorithm as a function of the input size, OK? So this is the runtime of DFS. OK, so first, the easy thing. This first line costs, there's no recursion anywhere. We're just initializing an array of size n, right? So this is just order of n, easy peasy, right? So the complication happens here, right? So if you write a recursive relation, you don't have like this nice symmetric tree. Like how this thing will look like really depends on the graph. Like you can't just like write down a tree and then use the kind of what's it called, the master theorem or whatever, right? It's just going to confuse you, right? Instead, what we want to do is to try to make some observation how the algorithm works, right? So look, explore will be run, several times. But one thing we certainly observe is that every vertex, how many times it is visited? Only once, right? Because look, here I visited at least once, right? And I will visit it once because that's what this says. It says if I haven't visited, I will visit it, right? Later, both inside here and here, if I've already visited, I will not do it again, right? So globally, I am visiting each vertex once. All right. But that's not really kind of all the costs, right? When I visit a vertex, I have some costs that depend on the edges, right? I may consider an edge and not explore it. I will consider an edge and then explore the other end. But just the act of considering it will cost me time, right? Because consider like a vertex that has many, many neighbors. All of them have already been visited. Just realizing that each one of them has already been visited and deciding not to recurse on them will cost me the number of edges, right? So I also have a cost that comes from the number of edges. So how many times will I consider each edge globally? Twice, right? Why? Because look, I will consider it once coming this direction, and the other time comes the other direction, right? But that's it. The edge has only two endpoints. And anytime I'm considering one endpoint to the other side, I've already marked that endpoint, and I will never come back to it again, right? So the running time is order of n plus m. OK? So you see, there was no recurrence relation. I'm just kind of observing that by kind of the way that flags are maintained and the way that the algorithm sort of keeps track of what it has done, I just did some global accounting with the observation that each vertex is visited exactly once, and each edge is considered exactly twice. There's no other work happening here. I've accounted for everything. Okay? Yes?
So the operations that you're counting are basically accesses to whatever data structure you're using.
Good question. So what are we counting? So right now, well, first it depends what the algorithm is, but let's see what the algorithm is doing, right? So this for each could be interpreted in different ways, right? You could say, I try to go through the entire line, which is basically what you would do here, right? Or in the adjacency list, you would just go there and read that list, right? So that cost is hiding the additional cost of basically for every edge, kind of incorporating it somewhere, sort of collecting its information from given the vertex, right? So one way to think about it is n times the cost of collecting the neighbors, right? Yeah?
Is it different between unrelated and related graph? What is runtime?
Sorry, I just want to take back what I said. Like, it's not n times. There is like, you have to do like a sum of these things. Okay, so it will be like roughly m times some constant or whatever is there. So it's a more difficult accounting. Sorry, I blanked out for your question.
Like, is this for the related graph or unrelated?
Excuse me?
Is this for the unrelated graph?
Oh, the question is this for directed or undirected graphs? Anybody want to answer? Both. So far, it doesn't really matter. Also, we're not doing anything yet. So, but in terms of like DFS marking everything, it certainly is the case that the algorithm doesn't care at this moment, right? Because it takes edges in a direction, right? When I am at V and I want to go to U, I am specifically going in that direction, right? Some other time, I may be at U and maybe trying to go back to V and realize that I was already there, okay? But right now, this one will mark edges properly, will mark vertices properly, both in undirected and directed graphs. Okay? This distinction will become important basically now that we start talking about connectivity, that we have to distinguish the two cases. Because we want to start using DFS for doing something useful for real. Okay? Okay. Okay, so it's, now that we have DFS out of the way, let's talk about connectivity. So let me actually write the running time of DFS here. And give myself space here. All right, so now we want to talk about connectivity in undirected graphs. So for many problems that we'll consider, the undirected case is going to typically be easier. It certainly is the case for connectivity. So what's the problem we're trying to solve? First, well, really what we want to do is, given a graph, we want to compute all the connected components. So what are they? Well, I need to introduce a relation, and we're going to say that U and V vertices are connected if you can go from U according to some path to V, which, because the graph is undirected, is also equivalent to going from V to U in some way. Okay? So first I want to say, let us define two vertices to be connected. If there is a path, maybe multiple edges, not just one, that let you go from U to V, but we're in an undirected case, so that is equivalent to saying there is a way to go from V to U, because you can just reverse all those edges, right? Now, the connectedness relation is an equivalence relation. It is reflexive, because you're connected to yourself. It is symmetric, because it is undirected. And it is transitive, right? Because if you go somewhere and you can go further on, right, you can certainly go all the way, right? Anytime you have a sort of equivalence relation, it partitions your set into so-called equivalence classes, right? So it means that your graph, your undirected graph, in fact, can be partitioned in connected components. These are vertices that can all go to anybody else in the same component, right? All we want to do right now is to just figure out what these are. Okay? You give me a graph as an input. What are the connected components? Okay? That's basic question. You can think about it some sort of like clustering. It's not really clustering, because clusters are more about, you know, closer versus farther away. But it's some sort of clustering. You want to just like chop it up in a way that no edges cut across, right? And the most number of components that with such property. Okay, so now what we're going to do is we're going to see a very simple change on explore and DFS that will achieve this. Okay? Any questions about definition of the problem? It's a simple problem, right? Okay. All right, so the algorithm connected components of G will basically get super tiny modification of DFS. It works as follows. So for every v in V, first we're going to set the visited flag to be false, like before. And now we want to add some bookkeeping, right? So what does it mean to find the connected components? Well, one way to find them is we assign to each vertex the name of its connected component, right? And at the beginning, we don't know what these names are. So we just say the connected component number of V is just, I don't know, null. Okay, I don't know yet what it is, right? I just allocate an array that will store my answer. All right, so then I want to start the algorithm. And I'm going to say, OK, look, let's have a counter that will kind of keep track which connected component are we at right now. OK? At the beginning, there's no connected component, so we just start the counter at 0. OK? And now we say for every V in V, OK, if not visited, then what does it mean? It means like we probably have come across a new connected component. All right? So we're going to say, OK, so let's increase our connected component counter. OK? And then explore from V. OK, but you know, inside explore, I probably need to do also some changes that kind of keep track of everything that I explore here. I should assign it this counter, right? So let's do it here. So I'm going to write explore again, but with a modification for bookkeeping of connected components. So like before, we're going to set the flag of visited to be true. And now, in addition, what should I do? I should set CC_num of V to be what? CC, right? Because that is my current connected component, right? So I just say, well, just store it there. And then, like before, for all VU in E, if not visited U, then I explore U. Now notice that when I run explore on V, CC is never changed. There's no CC++ anywhere here. And we know that explore GV will go and reach everything that is reachable from V, right? So all of those things will be assigned the same CC number. Only when it's done, and you return to the caller, you go back to the next one. And the next time you find a not visited vertex, you will increase the counter CC plus, right? So, and then you will do it again, but this time there will be like a new number. And by the time you're done, the array CC_num will contain the names for each vertex of the connecting components in which they're in. OK? Again, the only changes that we did to DFS was just to add this bookkeeping information. Bookkeeping here, starting counter, and maintaining it here. OK? OK? All right, this should be clear, right? Also, make sure I get calibrated. This you should have also seen at some point, no? How many of you have seen it? All right, so about a third. So it's actually good that I'm going through it carefully. All right, so however, very soon we're going to be discussing the underacted case, which is decidedly more complicated. And more generally, there will be a lot of questions you can ask about graphs that can be answered with, very simple piece of information, which is something known as, how do we call them in the book? The pre-numbers and post-numbers, or pre-order and post-order, OK? So what we're going to do is we're going to come back to DFS one more time, and we'll add some information that seems, I don't know, like boring. We're going to keep track of time, and we'll kind of mark when a vertex goes on the stack and when it comes out. OK, it will these are two distinct time periods. OK, I'll explain this now. We will see how this bookkeeping information actually directly gives us connected components, and it will give us other information later to solve other problems. OK. So, all right. So let's modify DFS one more time to keep track of time on the stack. Also, understanding this algorithm is generally useful in many problems, including on exams. And so, so pay attention. All right. So what I want to do is to maintain a global clock for time on the stack. I will explain what this means. All right, so DFS, we're going to modify it as follows. Again, we need to start by initializing some arrays. So for every v in V, as before, we're going to have visited v is false. And then we'll store two pieces of information per vertex. The pre of v, for now it's going to be null. OK? And the post of v is going to be null. We'll see soon this is the interval of time that v spends on the call stack. OK? So this is kind of the modification over the bare bones DFS. And then for every v in V, we need to start the clock first. So we start clock is 0. So that's this clock starting. And then for every v in V, if not visited, then we explore it. OK. OK, we haven't done much here. So let's look inside Explorer. What do we change? So explore GV. So now what's happening? We have come across V, and we haven't visited before. So now, we're going to do, I'm going to say, OK. I'm going to say visited is true, because we are visiting it. So this thing is. It's a bit better. So visited V is true. Why? Because we just visited it, right? But now, kind of, because we're visiting it, notice that we will not leave V until we are done exploring all kinds of things reachable from V, right? So the kind of the call explore GV will not return to the caller until we're done with all the things below, right? So we're going to say, OK, let's mark the time that V goes on the stack. So we're going to say pre-V is clock, whatever the clock is now. Because I've done an action, I put V on the stack, I should increment the clock. OK? Because the next time I mark the time, it should have done something. If I never change the time, then everything happens in an instant. I have no idea what's going on, right? So, so now I do whatever Explorer was doing before for every outgoing edge, VU in E, OK? If not visited U, then as before, I explore it. OK? And now, before, whenever we're done with this, with all of the outgoing edges, we explored all of the not visited vertices reachable from V, we would return back to the caller, right? Now, we should just remind ourselves that we wanted to keep track of intervals, right? So first, we're going to say, OK, post of V is clock, and we're going to increment it, right? And if you notice, these two additional lines keep track exactly of how long V was on the call stack. The stretching or a question? No.
Are we assuming that checking all these edges doesn't take any time?
Well, the question is, are we assuming that checking edges doesn't take any time? Well, we did sort of have a kind of an amortized analysis here that in globally, looking at each vertex either direction will basically, we look at each vertex once or each undirected vertex twice, right? And cumulatively, we call that M. Now, even DFS, before we had this pre and post, if you have a specific data structure where you need to collect neighbors with some cost, you're going to need to have to account it into your total cost here, OK? But I didn't do that here. OK?
What I meant is, we're not incrementing the clock counter every time we visit, or every time we check an edge, right?
No, because so the question is, don't we have a counter for the edges? We could. It depends on what bookkeeping information you're interested in. The bookkeeping information that we'll consider is related primarily to vertices on the call stack. Okay. It is true that you could assign a time to when a vertex is considered in one direction and when it is considered in the other direction, and you would have these two numbers kind of appearing in some array. I'm not too sure whether that gives you some insights. It certainly is sort of one could think about it. For the type of things we'll be doing, we won't be doing that. Good question. This also goes into algorithm design, right? So here we're presenting kind of digested material of like canonical problems. When you're out there designing algorithms by yourself, this is certainly something that is reasonable to consider. A priori, there's no reason why not. OK, so now I want to at least convince you that all this extra work at least did not bring us backward. What do I mean? At the very least, given this information, we can read off the connected components. Okay, so we did no worse than before. Okay? So let me put this up. So let's say reading off connected components. What does it mean? I ran this algorithm. It took linear time. Now I have these arrays of pre and post for every vertex. Okay? Now my question was, what are the connected components? Okay? And I didn't specifically tailor my bookkeeping for connected components. I want to kind of infer it from this information. So let me just maybe mention a couple of simple facts about pre and post that may make it clear kind of how the connected components are can be read off, right? So there we have types of intervals. So we can associate to each vertex an interval, right? That is the pre and post, right? Now let's say that I have an edge, UV, and it is really in the edge set. I have two intervals, the interval of U and the interval of V, right? And let's say this is time. How will these two intervals kind of relate to one another across time, right? So can they look like this? Can they look, I don't know, like this? Can they look like this? Is it clear what I'm saying? Like these are, when I run this algorithm, I have pre and post. Those are times in a timeline, right? And they define intervals, which I can visually represent using these brackets, okay? Like, could it be that I have something like this? Can the intervals intersect? No, right? That doesn't make sense, right? Because how could it be, right? I'm visiting you. V is reachable from you. In particular, it's an edge. I mean, it is reachable in one step, right? So I start visiting V. And like even before I'm done visiting V, I start popping you from the stack. Doesn't make sense, right? Sorry, yeah. Doesn't make sense, right? So this is not going to happen. The other way around also doesn't happen, right? So in general, these things don't intersect, right? Because it's the call stack, right? Like you have other things above to finish before you pop off the things below, right? Okay, so can they look like this? Yes and no, right? So if this is an edge, they really shouldn't look like that, right? Because if V is indeed reachable from U, it cannot be that I'm done exploring U, right, before I start exploring V, right? So this is a sign of something else that we'll talk about later, okay? So really what you should see is something like this, right? U, we put it on the stack, then V. At some point, you're done with V, and you start popping back, and then you pop out U as well, right? So it will kind of look like this. So let's maybe study this one, right? So this is the reflection of what? You have explored U, and you're done with U before you explore V. That means that V is not reachable from U. Right? So this may mean two things. Either it literally was not reachable from you, or maybe it was reachable, but it was marked already. Okay? It could have been, right? Yeah, I don't want to put down an example. But now let me kind of make some space and say the thing about the connected components. Oh wait, so the bare bones DFS, I think I can get rid of it, because at this point I have the upgraded one up there. Yet this point teaches us something, that these brackets, they behave like parentheses. They don't intersect, okay? When you open a parenthesis, okay, you're going to have to close it, but you cannot, in the meantime, open another parenthesis and close it after that one, okay? They behave like parentheses. So if you plot all the intervals, they will look something like this, right? No intersections, some nesting, and some juxtaposition, right? Let's say that this is literally what I get. How many connected components do you think there are? 3, right? Because look, here, like I'm not inside any parentheses, right? And I'm starting to visit some vertex, right? The only time that I'm done with it is when I'm done exploring its connected component, okay? Then I start somewhere else, something that was not visited. So I start some other connected component, and I'm done at some point, right? So if you look at the first level of parentheses, those are the connected components, okay? So kind of, you have 3 connected components. So this is to say that the information about the connected components is contained rather clearly in this pre and post orders, okay? How do you algorithmically do it? Well, you know, you can output them, you know, according to the stack order, right? And you start from here, right? And you move in this direction, and any other thing you find in the meantime that's in the same connected component, when you're done with the parentheses, you call that off, okay? And you continue, all right? So you can really read them off, the connected components. Yes?
Wouldn't the initial version be faster? Because what we store is just the time for pre and post. But if you want to actually like construct this, you have to, for each time, find whether we have a pre at that time or a post at that time, so we have to go over the whole pre and post array.
So maybe I'll leave this as an exercise. They will be the same time. Why? Because if you know that you want to look for connected components, as you run this, you can output things in an order that is already what you wanted. So you don't have to sort anything. Okay? So this entire thing can be done. This is an important point, by the way. When I write this timeline, and they appear sorted, yeah, you could in particular sort them, but sorting is, it's n log n, right? That is, you know, it's not a lot, but it is more than linear, right? And right now we're like, you know, running in linear time. But as you run the algorithm, as you pop things from the stack, you can output them, right? And things that are popped from the stack later, you will be outputting them later, right? So already things will be spit out in the order that you want, okay? Because this is not a total order. This is like an order. It's not like you started with a list and you're trying to sort it. You're just producing a list that has a certain ordering that, by the way, like it's kind of underspecified. That's why you don't really run into sorting kind of lower bounds. Like this thing could have also appeared there, and it would still have given the right answer, right? So somehow this list is not kind of really, you're not producing you cannot somehow twist this algorithm to magically sort things for you in linear time. It is not sorting. It is producing things in an order that contains information about connected components. Yeah?
So basically, as the first time you put something on the stack, you maintain a list, and whatever we see, we put in that list, and whenever the stack is empty, we say, this is the next, right? Because the stack is empty, it means we're done on
Yes, whenever the stack is empty is exactly those moments that you're done with a connected component. And you can keep track of that on the fly, and you can do this in linear time. But I encourage, like, there's only so much pseudocode I can put on a board, and at some point it will also become boring, not just for me, but for you as well. You probably want to clarify these things to yourself, like, you know, offline. Okay. All right. In the last 15 minutes, what I want to do is start moving into the directed case. And in the directed case, things are going to get a little bit more complicated. And starting with what does it even mean to run this algorithm on the undirected case. So I'm going to go through an example of how you keep track of the stack kind of on paper, because it's also something you may actually do in some exercises. Okay? But is it clear that what we've done is we looked at connectivity in an undirected case. We had a tailored algorithm first, running linear time. Now we have some other algorithm that is kind of doing more, and as a special case, we can read off the connected components, okay? This very same algorithm, without any changes, now we're going to run it on a directed graph, and it will give us some information as well, okay? All right. So here, all right. First, I want to run through a directed graph example on this algorithm to see kind of what kind of information you are storing. So bear with me. I need to put down some example. I forget if this example is even from the book. From my notes, I don't remember. So maybe you can even find it inside the book itself. So now notice that when I'm drawing the graph, I am the single direction of the arrows. It is deliberate because that is the direction of the edge. Oof. Okay, so make sure that I have the same one. Otherwise, I'm going to make a mess. All right, so this is a directed graph, okay? So now we're going to run this algorithm on it, which, like before, it is well-defined on any graph, including directed ones. What will happen is that we'll have intervals of time associated to each vertex, right? So we start at A. That means that A goes on the stack. I think the way I defined it, it will go at time 0, but let's just move everything one forward, so we'll kind of start at 1, okay? So A goes on the stack at time 1. It'll be a while until it comes off, but so now we start exploring. Actually, let me write it here. We start exploring. What do we find? You could go really any of these, but in particular, let's say that we're going first on B. It means that we start exploring B. So B goes on the stack at time 2. In the meantime, we incremented, right? From B, we say, OK, actually, B has only one outgoing edge. It has one incoming edge, but we don't care. We're just going out, right? So we go to E. So E will go on the stack at time 3, right? Now, E has 2 outgoing edges, to F and H, right? So we have to start with 1. In my notes, I start with F. So again, you could have started with H, but I'm starting with F. We go to F. Now, some interesting things start happening. First, we discover that there is an edge to B, but B has already been visited, right? So we can visually keep track of this and say, OK, look, there is an edge that I'm not traveling, but I did consider that goes back from F to B. OK? There's no operations associated to it. There's no time associated to that. So that's one of the things I consider. F also has an outgoing edge to G. So that one I should consider because I haven't been to G yet. So let's say 5. Now, G is pretty lonely. There's like no outgoing arrows. So the moment I put it on the stack, I realize there's nothing to do. So off it goes at time 6, right? So now I go back to the caller. The caller was F, right? I'm done exploring the outgoing edges of F at time 7, right? So now I go back to the caller. That was E, right? Now E has another edge that is H, right? So I explore H. What time is it? It is time 8, right? Now H has an outgoing edge to G, but G has already been explored, so I can just kind of keep track of that as an edge that I did consider but did not explore. And that's the only outgoing edge of H, so really no time has passed. So that's 9. Go back to caller, and I'm done at time 10. Okay? Go back to caller, that's B. AE was the only outgoing edge, I mean the only neighbor of B, so I'm done exploring B at time 11, right? Okay, that was only one branch of A. So now let's say that the next one is kind of F. So why do I have a forward edge somewhere. Sorry, I'm not going to put it there. No, yeah, I do want to put it here. I wanted to put an edge here to say that whenever I go back to the caller, I wanted to show a forward edge going down to I want to give names to these edges later. Okay, now I'm back to A. Now A has F as a neighbor, right? But F has already been explored, right? So I consider, but do not explore, the neighbor F, okay? Fine, so C we haven't seen yet, so we see C, and it's time 12. From C, I go down to D, which I haven't seen before, and it's time 13, right? At D, I have various outgoing edges. I have an outgoing edge to H, but I have already seen H, and I have a back edge going to A, which I've already seen, right? So I'm done at 14, done at 15, done at 16. All right. All right. This is the type of computation you should be comfortable with, right? It is a computation that, it's not so difficult to do on paper if you draw things out neatly. Now, I just want to kind of point out, some observations about the types of edges that we have here. So there are somehow edges that are part of the kind of main exploration, and there are some edges that were considered but not explored. Okay, these correspond to different types of intervals. Okay, so let's talk about those types of intervals. I want to also call let's give names to these things. So this is known as a cross edge. Why is it a cross edge? Because it goes kind of to something that is neither a parent, neither an ancestor, nor a descendant, okay? But it is reachable from the same ancestor, okay? So this is a cross edge. This we'll call a back edge, okay, because it is pointing to an ancestor. And this is a forward edge because this is pointing directly to a descendant. This is different from a cross edge, right? Because there is no direct path, elsewhere in the main sort of execution of the algorithm, right? Again, this is just, if I had chosen different order on which vertices to consider first in neighbors, I would have gotten a slightly different tree, okay? Some of these dotted arrows would have become solid. Other solid ones would have become dotted, okay? Yet, for a given execution, I can name each of the dotted arrows as either forward, back, or cross, okay? Because if you have an edge to some other node, it's either a descendant or an ancestor or neither, right? So it can certainly falls into one of these three categories. Now, these types of edges have different interval, they look differently. So a tree edge, so a tree edge is the one that is solid, kind of solid. We'll have intervals that look like, so let's say that UV is an edge in the graph, If it happens to be a tree edge, namely it is solid in a particular execution, then it will look like this, right? Which makes sense, right? I explored first U, then I got to V eventually. Maybe V was like further down the road, okay? Maybe we didn't explore it immediately. Maybe we explored another neighbor of U first, so maybe there's another interval here. But at some point, there's the interval V, and then we're done with U, okay? So then we also have forward edges. These are, yeah, forward edges. Again, they look the same, okay? U, V, V, U, okay? Because again, we kind of explored U, okay? And at some point, we did other things first, and we touched, for example, this one, and we came back. Like this is an example of a forward edge here, right? And E really is attached to G, except that G was explored in some other branch, right? And so, but nonetheless, I will be done with G before I'm done with E. So again, looks like that. A back edge will look like V, U, U, V, right? Because if UV is a back edge, okay, it means that V was the one that was being explored first, okay? So that's the outer one, the one containing it, okay? And then we have a cross edge, okay? So that means that, example here, G was done exploring, then we kind of went up, and then we went down somewhere else, right? So these are disjoint vertices, the disjoint intervals. It doesn't mean that they're in different kind of connected components, even though we haven't defined them yet. It just means that they're disjoint, right? Because in this example here, the fact that these two are disjoint does not mean they're in different connected components. You have to kind of look at the base parenthesis for that, right? It just means that there's a cross edge. U, V. Okay. Now, you may wonder, why did we bother going through all of this? This is just to build some intuition about things we'll do with directed acyclic graphs, okay? So this is just to kind of feel and see what these pre and post numbers mean in a particular execution. Because I guess primarily what we're going to do in the next lecture is we're going to talk about connectivity in directed graphs. And you see that because you're in a directed graph, there's a lot more information that kind of these pre and post numbers pack, okay? And the first thing we're going to have to tackle is what even connectedness means in a directed acyclic graph, because we don't have a symmetric relation, right? So we need a different notion. We'll have to introduce the notion of directed acyclic graphs. We'll have to kind of recognize when we have a directed acyclic graph. And pre and post numbers will be our friends, okay? So maybe in preparation for next lecture, encourage you to maybe try to run executions of this sort on your own and try to draw these execution trees, okay?